contains two gems. Okay. Good afternoon. Okay, so let's remember where we were at. Keep it down a bit, please. Hey, 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 hey! Sorry, thank you. Okay, so let's remember where we're at. We were talking about bases yesterday. So we showed in particular that every finitely generated vector space has a basis. I think it's coming out of there. The little one's broken, I think. Yeah. And this leads us on to the idea of dimension, but we're not quite there yet, actually, because what we've shown, and in the appendix you show all vector spaces have a basis using axiom of choice, but for now let's just think about finitely generated case. So there we have, by definition, that means the vector space has a finite spanning set, and then by reducing that down to a minimal spanning set, we get a basis. So it's definitely got a basis with finitely many elements, but what's not clear from what we did the other day, yesterday, is that all bases have the same number of elements. And that's what we'll prove today. Okay, so the main aim for today is to prove that every basis of a finitely generated vector space has the same number of elements. That leads to the notion of dimension just being this number of elements. And yeah. All right. Any questions? Okay. So there's two sort of results here. There's a replacement lemma, and then there's something called the replacement theorem. And these are both about if you've got a basis and some property, then you can replace some elements of the basis by some other elements. Is kind of the idea here. So how does this one go? So we've got a basis of our vector space. So actually here I'm not even insisting finitely generated, I'm just saying it's a basis. So this indexing set I could be enormous, we don't really know. But anyway, think of the finitely generated case. If we've got a basis and we've got an element which is a linear combination of these basis elements, and if that lambda j coefficient, say, is non-zero, then what I can do is take the old basis, throw away v subscript j, and throw in w. And in doing that process, I stay as a basis. Okay. So just to run through it again, you've got a basis, you've got a w written as a linear combination of those basis elements with lambda j, let's say, being non-zero. Then you can throw out v subscript j and throw in w, and you stay a basis. All right. So the way that one works is as follows. So we'll just show really directly that B is a basis by checking the definition of a basis. It needs to be a linearly independent spanning set. So first, B prime is linearly independent. So let's prove that. Because if I have a linear combination of elements of B, so that's something like this. So J is the thing I've thrown out. So if that's a generic linear combination of elements of B prime. If that equals 0, then, well, remembering what W is and grouping everything back together, we get mu lambda J Vj plus sum over I, but not J. Oops, not J. Okay, so all I've done there is replace W by its linear combination over there on the left screen. But this is now a linear combination of elements of B, and B was a basis, so B is linearly independent. So that means mu times lambda J has to be 0, and all the other ones 0 as well. But the first one there, remember that lambda J, that was part of our assumption, lambda J is non-zero, so that means mu has to be 0. But then the second equation tells us that all of the mu i's are 0 as well. Okay, so that verifies linear independence. So if we have a linear combination that equals 0, all of the coefficients had to be 0. And the next thing, of course, is we have to show that B is a spanning set. B prime, sorry. Okay, so to do that, if we have any old vector in V, so because B is a spanning set, we can write V as a linear combination. But I just want to now turn that into a linear combination in B prime. So of course what I have to do is take the V subscript J element out and rewrite that in terms of W. So Vj was, so what was that again? So I'll write it over here. W was the sum I in I lambda I Vi. So Vj is lambda J inverse W minus sum I in I but not J, lambda J inverse lambda I Vi. Okay. Again, by hypothesis, the lambda J was non-zero. Good. So plugging that one into the other one, so call that 2 or something. Plugging 2 into 1 gives V as a linear combination of elements of B prime. So we're done. Okay, so just straightforward kind of little thing. Any questions about how the proof went? All right, good. So the next step is to beef that up to not just taking away one element and replacing it by one element, but taking away a whole heap of elements and replacing them by some other linearly independent set. So that one's called, so beef it up a bit, that one's called replacement theorem. So this is quite handy, this theorem, at a few places in the course. You often use it if you've got a basis for a subspace to extend it to a basis of the whole space in a nice way. But here's what it says. So we've got a subspace of our, we've got a basis of our space B. At a certain point when I was writing some of the future lectures, I thought I might change the notation and write curly B or something under there for the basis. I don't know. Anyway, doesn't matter. To not confuse with matrix B. Anyway. Okay, so if that's a basis of B, and if I've got another linearly independent set, W1 up to Wn. So again, actually in this theorem, there's no hypothesis on finite dimension, but there is a hypothesis there that this subset W1 up to Wn, that's a finite set because it's only up to n. Okay. But anyway, so the basis might be infinite at this stage, but I've got a finite linearly independent set, and I just insist on n being less than I, but it'll have to be because, well, no, we don't know that yet. Sorry, we don't know that all bases have the same number of elements, but I'm going to put it as a hypothesis. Then the point is I can find some subset of my original basis, namely here they are, the VJs with J and J, and I'll take those out. Okay, so there's some subset of these guys. I throw them away, and I put in these guys here, and I stay as a basis. So again, note that I'm taking away the same number of elements as I'm putting back in. That's kind of important in the way the theorem goes. Okay, so just run through it again. You've got a basis, you've got a linearly independent set, and you can find a subset of the original basis of the same cardinality as that linearly independent set, such that when you take those guys out and throw in this new linearly independent set, you get a basis. All right, how does that one go? Well, looks like an induction using the replacement lemma, and indeed it is. So it's induction on n, which is the number of elements in this linearly independent set that I was trying to put into the basis. And if n is 0, then there's nothing to prove. Or if you like, if n equals 1, it's the replacement lemma, but even easier, n equals 0 to start the induction. Okay, so by the induction hypothesis, there's a set which I'll call J1, subset of the indexing set I, with n minus 1 elements in it. Such that the set B1, which is obtained by throwing away all of the VI's with I in J1. So that's what that means. Throw away the VI's with I in J1. And then throw in the W1 up to Wn minus 1. This guy's a basis. Okay, so that's just the induction hypothesis, and then to get the next step, the n+1 step, so to speak, or whatever, is the replacement lemma. So let's do that. So since this is a basis Wn, this next guy in the linearly independent set, B1 spans the space, so this is a linear combination. So a generic linear combination looks like this. Linear combination of elements of B1. And the first thing I want to say, or the next thing I want to say, is that one of these coefficients here has to be non-zero. Why is that the case? I'm asking you, sorry. Yep. Why is one of these lambda i's not zero? Yep. Yeah, exactly. The W's are all linearly independent. If all of these were zero, then Wn is actually a linear combination of the other W's, and that's so we have to somewhere use linear independence of this subset W1 up to Wn, and this is where we're going to do it. One of these is non-zero. I call it J in my notes. I think so. Yep. And so now we're in a situation where we can use the replacement lemma. We can take, so this lambda j is non-zero, so we can take away the corresponding b subscript j, throw that out, and throw in wn instead. So I'll make this new set. I'll now throw away, I'd already thrown away J1, but now I'm going to throw away a bit more. I'm going to throw away J as well. So put brackets in to make it clear what I've done there. Okay, so I'm throwing away one extra thing, and I'm throwing in one extra thing, which I'll put over here. Okay, so again, kind of simple enough in a way, but you have to be a little bit clever how you set up that lemma feeding into the theorem. They sort of work so quite nicely together. Okay, good. Now, any questions? Today, proofs, you just fly through the proofs. Okay, so the corollary, the important corollary, is that every finitely generated vector space, well, in a finitely generated vector space, every basis has the same number of elements. Okay, something which you of course take for granted, but this is where we're going to prove it. Okay, so that one goes as follows. We said the argument here is going to be, suppose we have two bases with one being strictly bigger than the other, and then we'll sort of use the replacement theorem to start with our bigger basis, and we'll sort of include the smaller basis and throw away some other stuff, and it'll contradict the minimal spanning set business. That's the way that's going to go. So let's write it out. So suppose we have two, so suppose for a contradiction, we'll suppose we have two bases of different sizes. Has bases B being V1 up to Vm and B prime V1 up to Vn prime. And let's say n is strictly smaller than m. Now, by the replacement theorem, there exists a subset J of the indexing set for the bigger one, which is 1 up to m. Let's call that I. With n elements. Such that when I throw away those elements, and throw in the other elements, we stay as a basis. But the problem here is that this B prime was a basis and therefore a maximal linearly independent spanning set by the characterization theorem. And this is saying we're throwing in some more stuff and staying linearly independent, which is a contradiction. Okay, great. So that's out of the way now. So all bases of finitely generated vector spaces have the same number of elements. Yep. It's the therefore part that doesn't follow. So just to say that two minimal spanning sets have the same number of elements, I mean, you need to prove that. So why would two minimal spanning sets have the same number of elements? Yeah. Yeah, it's a bit funny because, you know, I think you...
wouldn't there only be one minimum though?
No. There's lots of bases, first of all. Okay, so vector space has lots and lots of bases. For Rn, let's say, just to go to something concrete, Rn, take an invertible matrix, any old invertible n by n matrix, and take its columns. That's a basis of Rn. So there's infinitely many of those choices. So there's infinitely many bases, infinitely many minimal spanning sets, infinitely many maximally linearly independent sets. I think it's all the same thing. And there's no reason to begin with that they're all going to have the same number of elements. And that's what we had to prove here. But yeah, it's a bit like it's drilled in, I mean, because you learned a bit of this last year, of course, it's drilled into your head that bases always have the same number of elements. Well, the dimension makes sense, that you can talk about an n-dimensional space. But you just can't talk about an n-dimensional space until you prove this theorem. Yep.
So for example, if you had a vector space Z2 squared on Z2,
yep.
I can think of one basis, which is 1, 0, and 0, 1, but are there any others?
1, 0, 1, 1. 0, 1, 1, 1, and that's all. Yeah, 3 bases there. That tiny vector space Z2 squared has 4 elements in the vector space. It's a very small vector space, only finite vector space, 4 elements. And to have a basis, you just need to pick 2 non-zero vectors for that one, for that space. So you've got to avoid picking the 0 vector, and you've got to make choices from your other 2.
So 3 choose 2 equals.
3 choose 2, but that'll give order. It depends if you're on an ordered basis, because when we come to write out matrices of linear operators with respect to bases, we'll actually be not just fixing the basis as a set, but fixing the order, which basically gives us the order of our columns and rows. So if you think of ordered bases, then 1, 0 and 0, 1, and swapping them around will give different matrices. So they're kind of different bases as ordered bases, but they're the same as sets. Yeah, good. Yeah.
So, just trying to make sure I get the pictures for displacement here. So, like, if you have 2 bases and there's some like set of vectors from one of the bases where you can use those to replace vectors in the other one, and it'll still work out.
Mm-hmm. Yep, that's what the replacement theorem is saying. Replacement theorem is saying you've got a basis, boom, there it is, all those elements, and you've got a linearly independent set over here. And what it's saying is in your basis you can find a certain number of, you can find certain elements, the same number as you have in your linearly independent set, such that if you take those ones out and now bring your other linearly independent guys in and put them there, you stay as a basis. That's what it says. And as you see, it has this consequence that we just proved. Yeah.
We have to choose a specific choice of those vectors that we're taking out of the bound.
Yeah, that's right. You can't just, exactly. So you've got this linearly independent set, W1 up to Wn. You don't get to choose freely which ones you're going to take out from your basis to replace. What the theorem says is there exists elements that you can take out and replace. It doesn't tell you how to find them. But you sort of do know how to find them by the replacement lemma, because that just said if the guy in the replacement lemma where we were just popping one thing in and taking one thing out, the thing you could take out was just anything which when you wrote your new element W as a linear combination of the basis, it had a non-zero coefficient on that basis element. And then you could take out that basis element and put W in. And so sort of inductively, because we proved the replacement theorem by induction, so inductively you can actually find which things to take out. It's not unique which ones to take out, but you could work out which ones they are. Yeah. Good. Yep. Okay. So all bases have the same number of elements. It's also true in an infinite dimensional thing too that all bases have the same cardinality, but I don't know. I'm not going to talk more about that. So like uncountable, count, whatever the cardinality is in terms of all that stuff. But that's good. Okay, so at least the notion of dimension, so I've already used dimension when we've been explaining things in the first 3 lectures or whatever we've had, but really it's only now that we can properly define it. So the dimension of a vector space, we'll just call it infinity if the space is not finitely generated, so it's got no finite set which spans it. And otherwise, in our finite dimensional case, which is what we're mainly looking at, I must say, we'll just call it n if it has a basis with n elements. And of course, the corollary tells us that it's actually well defined. Okay. A remark here, sometimes we'll write dimension with a subscript of the field to really emphasize, especially if there's any ambiguity whatsoever as to what the base field of the vector space, what the field of the vector space is meant to be. A good example is dimension of C. If I just write dim C, well, unless I've explicitly said what field I'm considering C as a vector space over, then I can't answer the question. So if it's considered as a real vector space, so C as a vector space over the reals, what is its dimension? 2. Yeah, 2. And here, what's the basis? Yeah, exactly, 1i. So every element of the complex numbers can be written as a plus ib. So there you go, there's a basis. And they're linearly independent because if a plus ib equals 0, then equating real and imaginary parts, a is 0 and b is 0. Yeah. Yeah, it's actually ruled out by this proof here, because in the proof, okay, sort of in the proof I wrote ... Let's just, I could replace this one by this one. This one could have been allowed to have been finished here. There was no problem with that because it's always, the point in the replacement business, you're always taking a finite number of elements away, perhaps from an infinite set, but that'd be fine. So this set I, which I call 1 up to m, yeah, sorry, I probably should have written it that way. This one I could allow it to be an infinite set, possibly, then let the proof flow as it goes, and it obtains the contradiction. So if there's at least one finite basis, then all bases are finite and they have the same number of elements. Yeah, good. Yeah, so the proof's sort of written where it hides that a tiny bit, sorry, because I made it look like B had to be finite. Good. Yeah, good. All right. Dimension of C as a Q vector space. Yeah, infinite. It's not like, so if I really want to prove that, I could try to exhibit an infinite linearly independent set. That would be the way I could really do it. And I can, like if you take root 2, root 3, so I can even do R. Just replace the C by an R. Even. So the dimension of R is a Q vector space. But it works for C as well. But take root 2, root 3, root 5, root 7, root 11, root 13, the roots of all the primes. And you can prove without too much effort, but it's not, well, with some effort, I should say, it's not immediately, it's not a super easy proof. You can show that they're all linearly independent over Q. So if you take a rational combination of root 2, root 3, root 5, root 7, root 11, root blah, 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 put them all out in a big sum, set that equal to 0, then all of those coefficients have to be 0. So you can prove that by an induction kind of thing. Because you only got finitely many coefficients, not 0. So that shows that there's a linearly independent set which is infinite. But remember, a basis is a maximal linearly independent set. So we've got one that's infinite, so a basis has to be infinite as well. So that's something to emphasize. As soon as you find an infinite linearly independent set, you've got infinite dimensions, okay, by the characterization of it being a maximal linearly independent set. Right? But I'm not going to actually go through the details of that. I'm just going to, I mean, alternatively, in your mind, you've got to think, if this were finite dimensional, then there'd be finitely many complex numbers, there's finitely many of them, such that every other complex number in the universe can be written as a linear combination of those finitely many complex numbers with rational coefficients. And that seems ridiculous.
Which corollary is this talking about?
This corollary is a corollary that says all bases have the same number of elements. Otherwise, this doesn't make sense.
Okay, no, the reason I'm asking is because, like, so if for any vector space V which is not finitely generated, do we just attribute infinity in this sense?
It's infinity, yeah, in the definition.
Okay, so we don't look at this the same way we look at complex, right?
Yeah, I'm not distinguishing between uncountable, countable, or out of 1, 2, 3, 4s, and all that kind of stuff. We're just going to say infinite dimension. And that's just another word for not finite, somehow. Okay, so anyway, the point I'm saying here, this is infinite. Another way of doing it is like a counting argument of saying that this is countable and this is uncountable. And if you have a finite basis, then you've got finite sums of countable coefficients, so that would be countable. So C would have to be countable, but it's not. So that's probably the easiest way of seeing it. Okay. Anyway, I say C, it's in the tutorial, I think. Anyway, it should be, I want it to be obvious, so I shouldn't have carried on too much about it. Dimension of F superscript n? Not 1? N, yep. So remember what this is, emphasize what this is. This is column vectors of length n without elements of this. So the basis would be 1, 0, 0, 0, 0, 0, 1. That gives out a basis, and it's got n elements. What about the polynomials of degree less than or equal to n? N, but be careful because they start with the constant term, so it's n plus 1. Like the quadratic polynomials have constant term, linear term, and quadratic terms. So three degrees of freedom. Dimension of all polynomials? Yeah, certainly. And so this I'll say since 1x squared is infinite, linearly independent set, and basis, it is actually a basis in fact, and basis is maximal. So I should have just said that it's a basis actually. Oh, no, I'll leave it what I, anyway. See, the point I'm trying to make by writing it like that is I'm trying to say as soon as you find infinitely many linearly independent things, that means you've got infinite dimensions. Okay. This is continuous functions from R to R. Yep, good. Infinite dimension is a real vector space. It's infinity as well. And that would be, you find, again, infinitely many linearly independent functions. So you could take all of these ones. Oops, 2, 3, 4, 5, 1, 0, -1. You could take the ones that go like this. That's continuous. And then you could take another one that goes like this. These are their graphs. I don't know what I did. Maybe I should go one thing at a time. Take all of these functions. They're all continuous, that's why I've drawn them as little, not just as pointy, I have to make them continuous functions. They're all linearly independent because if I took a sum of such things, I just evaluate that big sum, that function, at these midpoints here, and it'll pick up just that coefficient because all the others are 0. And just that. Okay, so you've got an infinite linearly independent set. And then
so if but like, there's other ones that are infinite, but they have like a finite limit, like the polynomials.
this still doesn't have a finite basis. That's infinite basis. And finally, this one? 2n, good, 2n. Why? Because, I mean, just sort of roughly speaking, but maybe you, as an exercise, write out a proper basis for it. But roughly speaking, how many real numbers do you need to describe a vector in Cn? Well, you need, of course, Cn has the n complex numbers, but each complex number is 2 real numbers, so at the end of the day, you need 2n.
But isn't it like for the...
So, but I'll leave it to work, to be convinced that it's really 2n, write out a basis of this as a real vector space. Yeah. Oh, yep. This thing here. This is the vector space consisting of all continuous functions from the real numbers to the real numbers. And if these were functions f1, f2, f3, I've just drawn their graphs rather than writing out the formulas. So there's f1, f2, f3, and so on and so forth. I take some linear combination of all of those. I like to check and set it equal to 0. And to know that all the coefficients were 0, I just evaluate that function at these points. So I'll isolate. Blue and the, red and the green function are both 0 at this point, but the black function is 1, and so on and so forth.
Yeah, wouldn't we be able to use the exact same argument as in example 3, because that's still, they're all linearly independent? And
Just saying polynomials are good. Yep, you could say take the actual honest to God polynomials in there, they're continuous, and that's already got infinite dimension. Good. That's another way of saying it. So that would be, instead of taking these functions, taking the polynomials 1, x, x squared, x cubed, x3, that's linearly independent too. Yep, perfect.
that to show that it's the basis of the, sorry, not the basis. Is it to show that it's the field of the vector space?
Which part do you
Like in 4 and 5 we have dimension R.
Oh yeah, sorry, yeah. So that's up the top of the screen there. Let's slide down there. So we sometimes write dim F V to emphasize what the underlying field is. If we write just dimension of V, dim V, it should be clear, there should be no ambiguity what the field is, but if there is any possibility of ambiguity, I'll write the dimension in, and maybe I'll just, write the F in, and maybe I'll just basically always do it anyway, so I'm not sure. All right, but we've just got really one thing left to say for today. So the following is useful and used a lot, and you'll probably just use it without really referring to it, or without thinking about it. So we're in the finite dimensional case to make these kind of statements, and we've got a subset B of V, not a basis, just subset. Then first of all, if B spans V, so it's sort of got half the condition of being a basis, then B has to have at least n elements. Okay. So obvious, right? Because if it has less than n elements, then it can't be a basis. So it won't be spanning B. But we'll prove it in a second. So as at least n, and moreover, equality holds if and only if B actually is a basis. So what they're saying is, just say that another way. If you find a spanning set that has n elements, then it's a basis. Maybe that's the useful way of using that statement. And the second one is similar with linear independence. If I have a linearly independent subset, then it has at most n elements. And equality in that inequality holds if and only if B is a basis. So another way of saying that, if I find a linearly independent set with exactly n elements, and n is I know that n is the dimension, then it's a basis. So just say that one more time. If you know it's got the right number of elements, you only have to check one of the two conditions for being a basis. Okay. Maybe we've got a few minutes, so let's prove one of them at least and leave the other one as an exercise. Okay, so how we do this? So I think we'll note that if B spans V, then there is a subset such that B prime's a basis. Why is that? For that, I'm thinking of the minimal spanning set condition characterization. Okay, so if B spans V, then if I can remove anything, then I do it, and I just keep removing. If it still spans, I eventually get to a minimal spanning set, hence a basis. So anyway, that already tells us that n, which is the cardinality of B prime, because all bases have the same number of elements, is less than or equal to B. Okay, so that's sort of one way of saying that n is less than or equal to B. And now I have to make the statements about equality. Yep. So if B, when I start with it, if that has the property that removing any element, it fails to be a spanning set, then B is a minimal spanning set, hence a basis. But if there is one, then I remove an element and it still spans. And I keep going and I keep going, but it's a finite set. Sorry, I think I have to say B is a finite. Well, B is infinite, then there's nothing. Yeah, we don't have to do it. Yeah, so if B is infinite, then the inequality is fine. Right? But yeah, if B is a finite set, then we can just keep removing things and check. I removed that guy. Is it still a spanning set? If so, well, indeed, remove it and take that new set and see if I can remove anything else. Keep going. Since there's only finitely many elements, eventually I hit the wall where I've got a spanning set, and removing anything stops me being a spanning set. So that's a minimal spanning set, and hence a basis. Yep. Okay, to prove the equality statements, we need to show well, let's sort of break it up. It's quite a few things. We have to prove that if B is bigger than n, then B is not a basis. Well, really, if and only if. And we have to prove, secondly, that if B equals n, then that's the same as B being a basis. So let's prove both of those. Let's break them up. So I'm trying to prove equality if and only if. So it's sort of these two. This is what equality if and only if means. It's these two statements. All right, so the first one, if I try to prove this direction, let's say. Well, if B, let me just get started. If B is bigger than n, then B not a basis, as all bases have the same number of elements. By our corollary from earlier. And conversely, if B is not a basis, then it implies that I can remove things. And so n, which was B prime, is strictly less than B. Okay, so again, it's this idea of reducing to a minimal spanning set is used quite a lot. Okay? There I'm used it again, so my B prime from what I was talking about earlier is a strict subset, so it has strictly fewer elements, and so on and so forth. So the next one, I have to prove, we're almost done, so I have to prove that if B equals n, then that implies that B prime has to, the number of elements of B prime has to equal B. So B is a basis, where B prime again is this minimal linearly independent spanning set I found. And the other one should be clear, I guess, so B is a basis. Indeed implies that B equals n from the corollary. Okay, now the second statement, which was called 2 or something, is an exercise. So maybe I should have called these A and B here. I'll just quickly do that. Okay, good. Any questions about all of that? So dimension, super important. We've done it very rigorously. As I say, you've got this non-examinable appendix, if you like, with axiom of choice stuff. Okay, I'll see you on Thursday for the practice class. Yeah, so, okay, so see the tutorial for that. Answer that in the tutorial. All right, go. Good.
So, from the example yesterday about E and I being independent,
Yep.
is that related to them being transcendental, or is it
It's not equivalent to them being transcendental. It's something about them being, because it's something about them, are they linked to each other? So something like, like, for example, E and 1 minus E. They're both transcendental numbers, but I can do E plus 1 minus E, and that equals 1. Yeah, so,
is the proof that they're transcendental like beyond this course?
yeah. The proving E and pi are transcendental is pretty hard. I think E's like the easier of the two, and then pi is a real pain, I think. And yeah, but the things that you, well, if you ever need it, I would tell you that it's true. You know, I wouldn't, but you're never going to prove it. the reason being, not because it's, you know, it's like a rather, it's an important result, but it's quite sort of isolated in a way. It's not part of a bigger course or whatever. So to take 2 weeks or something to go through that proof probably won't fit in. In third year, you'll use the fact, I guess, that, or you'll maybe state the fact that E and pi are transcendental when you're looking at the Galois theory, when you're talking about field extensions, but you still won't prove it. Because it doesn't really fit into that. It doesn't use the, you know, it's a very specialised niche result. And, well, yeah. No worries. Okay.
What's your office hours for this?
Yeah, Monday, 2 o'clock. Excellent.
Thank you.
Okay, no worries.
I just have a question. So the example of like the dimension of c to the n over the rational the dimension being 2n, would that, because I'm not sure if I understand it correctly. I tried writing a base. Would it just be like like n? You would have n elements where each one is like a complex number, because I don't really understand.
No. So your basis would look like.
I tried to read that.
So basically, so first of all, if it was just Cn as its complex vector space, maybe we have to go outside in case it's another pass anyway, but I'll explain it later.